Welcome to the thermodynamic principle and corrosion aspect of refractories under the edges of chemical process utility. Now, before we go into the detail of the thermodynamic aspect of refractories, let us have a brief outlook about the topics which we covered in the previous lecture. So, previously we discussed about the introductory aspect of refractories. In this era we discussed about the important requirement for uses and pertaining to the classification of refractories. Then we discussed about the properties of refractories. When we were discussing about the properties, we segregated the properties in three different spectrum. Physical properties, under the physical properties we discussed about the density, porosity, abrasion strength, etc. Whereas in the thermal properties we discussed about the thermal shock, thermal conductivity, thermal diffusivity. Then we discussed about the chemical properties with respect to the erosion and corrosion, and apart from this we discussed about the various ceramic properties, and we started that particular lecture about the production of refractories concept. Now, in this particular lecture we are going to discuss about the concept of production of refractories. Under this we will discuss about the firing aspect. Then we will discuss about the thermodynamic principle, because this is the you can say the theoretical backbone of the refractories. Under this aspect we will discuss about the free energy, enthalpy, entropy, chemical equilibrium, chemical stability, all these things we will discuss. Then we will discuss about the different stages of corrosion, like stage 1 corrosion, stage 2 corrosion and stage 3 corrosion. So, let us start with the firing. Now, it is the final stage in brick making, and formerly beehive kiln were used for firing. Now, newly developed furnace, those who are used today, number of furnaces, they are arranged side by side. Since during the firing oxygen is the key component, and usually the oxygen is whatever oxygen is required for burning is usually supplied through air. Now, after passing through the firing furnace, the high temperature air is passed through those furnaces that are to be heated for firing. Now, by this way the waste heat utilization takes place. Now, second type of furnace used for firing is the similar to the tunnel kiln, which we discussed in the previous lecture, and that is used for the drying. Now, in this the stock moves tunnel kiln are thermodynamically very efficient counterflow heat exchanger. The firing zone is in the middle of the kiln's length, and the secondary air enters from the exit end. Now, at the firing zone, the oil burner, they usually operate with the help of oxygen in the preheated air. Now, from the firing zone, the combustion product, they carry heat and pass through the preheating zone. Now, as the green bricks pass through this particular zone, they absorb heat from combustion products and they are preheated. The firing temperature is usually maintained at least as high as the working temperature for sufficiently long enough to ensure that all possible reactions are completed and that dimensional stability is attained. Now, in recent year the in situ firing has been introduced, that is, the bricks are not separately fired. The green bricks are made and equipment such as furnace is built. Now, during the operation of furnace, the bricks get fired. Now, here you see that this is the tunnel kiln here. Now, as we discussed in the previously, there is a preheating zone and a firing zone and a cooling zone, and the movement usually goes in this particular direction. Now, in this this particular figure shows the cross section of firing zone. Here you see that this is the gas or oil burner, and with the help of a sand seal. Now, let us discuss about the thermodynamic principles. The refractories are meant to be exposed to high temperature, and that causes many changes which are the result of the refractories reaction with the environment. The environment can be in the form of solid, liquid or gas. The reaction take place where the refractories and environment make contact. The thermodynamic principle helps in predicting which reactions are impossible based on changes in free energy. Now, it is obtained by subtracting the free energy of the reaction from the free energy of the product. Now, in case where the free energy change is positive, it is impossible for such reaction to take place spontaneously. Now, this happens because any system will try to acquire a state of lowest energy. Therefore, the free energy becomes an important term in the field of thermodynamics. Now, let us talk about the free energy. Now, what is defined by free energy? This can be seen in the Gibbs free energy function, which consists of two terms, enthalpy and entropy. Let us have a brief outlook about the enthalpy. The enthalpy of a compound at any temperature is its heat of formation from its element at that particular temperature. Now, at constant pressure, the enthalpy of a substance can be defined as the heat absorbed or released by it. Now, enthalpy, you can write the enthalpy as H1 is H minus H298, that is 298 Kelvin temperature, is equal to 290 integration 298 to T Cp dt, and that is equation number 1. Now, Cp is the heat capacity at constant pressure, which can be written in the form of change in enthalpy with respect to temperature at constant pressure. Now, Cp you can represent as Cp is equal to dH over dt at constant pressure, that is equation number 2. Now, if we integrate this equation at two different temperatures, say from T1 to T2, or the standard temperature 298 Kelvin and T, the equation for enthalpy can be obtained. Now, another equation connecting the temperature and Cp. Now, Cp is equal to A plus Bt plus Ct square, C over T square. Now, A, B, C are constants. Entropy, it measures the degree of disorder in the system. Higher the degree of disorder, higher will be the entropy. Degree of disorder increase with the amount of heat absorbed by the system. Thus, entropy at any temperature is given as the ratio of heat absorbed reversibly by the system and the temperature. So, in a broad spectrum, entropy can be written as, or entropy can be represented as S is equal to Q over T. In the microscopic zone, the Boltzmann equation preferred where K is constant and omega is the measure of randomness. So, it can be represented as S is equal to K ln omega. Now, entropy can rise by the different means, which of them follows, like configurational entropy and represented as SC. Now, this is related to the different configuration of atom in a crystalline lattice. Then thermal entropy ST, this arises from the thermal energy levels possessed by the atom. Then electronic entropy, and that is represented by Se. This is associated with the electrons. Then the magnetic entropy Sm, this is related to the magnetic moment. Then the dielectric entropy Sd, this concerns with the dielectric moment. The total entropy is the sum of all of them. That is, the total entropy of a system can be obtained by addition of different entropies or entropy value it possesses, like S total is Sc, St, Se, Sm plus Sd. Let us talk about free energy. Now, the free energy determines the stability of any system, and the stability is associated with equilibrium. Now, at equilibrium, the system will be at its lowest free energy value. The free energy is determined by the equation G is equal to H minus Ts. Now here the S represents the total entropy of the system. Now if any changes or any change take place in the free energy at constant temperature, this particular equation can be written as delta G is equal to delta H minus T delta S. So now here at equilibrium, the change in the Gibbs free energy, and this delta G refers to be the change in Gibbs free energy. So at equilibrium, the change in the Gibbs free energy with the extent of reversible reaction psi, this can be seen in this particular figure. Now at equilibrium, it is quite evident that delta G is equal to 0. Now let us talk about the chemical equilibrium. It is associated with the chemical equation. Now to explain, let us consider a chemical reaction. Let us say that half X2G, that is in the gaseous form, plus M is in the solid form, and it gives you Mx in the solid form. Now this total gives free energy change for the above equation. This can be written as delta G, that is the change in the Gibbs free energy, is equal to delta G naught minus RT ln K. Here this delta G naught is the free energy change when reactant and product are in their standard state, and K is the equilibrium constant for the reaction. Now the equilibrium constant K for this particular reaction can be written as K is equal to AMX over AM into Px2 to the power half. That is the mass action expression. Now at equilibrium, as we understand that there is no change in the free energy, and that is delta G naught is equal to minus RT ln K, and K is given terms is the standard free energy change, and it can be expressed as K is equal to exponential of minus delta G naught over RT. Let us talk about the chemical stability. The solid material are chemically stable when their activities are within certain range of values. That is, the refractories process activities such that they are stable in oxidizing condition. The range of activity values in which material is chemically stable is the chemical stability domain for the material. With the help of thermodynamics, we can calculate the stability domains. Now let us consider the oxidation of any metal M. Now if it forms two type of oxides like MOZ and MOY, and Y is greater than Z. Now consider the oxidation reaction of M to form its lower oxide, and that is M plus Z by 2 is equal to MOZ. Now let standard free energy for this particular reaction be delta Gi naught. So we can write the partial pressure of oxygen as Ln PO naught is equal to 2 Gi naught over ZRT. Now further oxidation of MOZ gives MOY, and that is 2 over Y minus Z into MOZ plus O2 is equal to 2 over Y minus Z MOY. Now corresponding partial pressure of oxygen can be represented as Ln PO2 is equal to 2 G2 naught over ZRT. Now here G2 naught value is given as G2 naught is equal to 2 over Y minus Z GMOY naught minus G1 naught. This G naught represents the standard condition. Now in this equation, GMOY naught delta GMOY naught is the standard free energy change for the formulation of MOY. Thus, the chemical stability domain for MOZ at temperature T is in between the partial pressure of oxygen corresponding to delta G1 naught and delta G2 naught. Now let's talk about the corrosion of refractories. Now refractories are used at elevated temperatures for structural purpose, and they are used in many cases to contain a high temperature corrosive environment. Now this corrosive environment usually contains liquid, that is in the melted phase, and that participates in chemical reaction with the refractory at elevated temperatures, resulting in refractory consumption or wear. The oxidation and reduction state of environment can participate in and influence chemical reaction. During this particular chemical reaction, the physical changes occur that may be accelerated by the corrosion process. Corrosion of refractories is the refractory wear by loss of thickness and mass from the exposed face of the refractory as a consequence of chemical attack by a corroding fluid in a process. Now, in this particular, the refractory and corroding fluid react together and approaching the chemical equilibrium in the zone of contact between the refractory and the fluid. The phase equilibrium diagram, this can be used to analyze the corrosion situation and to predict the chemical strategies to minimize the corrosion and wear rates. Now, while we are discussing the corrosion, then let's talk about briefly the fundamental principle of corrosion. Now, there are fortunately a few fundamental principles that the investigator can apply to any corrosion situation. Now, first fundamental principle on refractory and slag compatibility. The first fundamental principle is that acid refractories tend to resist acid slag better than the basic slag, and conversely the basic refractories tend to resist the basic slag better than acid slags. The definition of acidity and basicity in room temperature solution of any kind of refractory chemistry at elevated temperature have the key difference. Now, the definition of acidity and basicity in solution chemistry at room temperature. Now, acid contains an excess of hydrogen ions H plus over hydroxyl ions OH minus, considering the baseline defined as neutrality at pH of 7. Now, an acidic substance contributes hydrogen ions to chemical solution to make it more acidic, whereas a basic substance contributes hydroxyl ion to make it more basic. Now, an acidic material contains an excess of silica content SiO2 over basic material, usually in this case calcium oxide, considering a baseline defined as the neutrality at Ca over SiO2 ratio of 1. Now, an acidic material contains an excess of silica content SiO2 over basic material, usually in this case is CaO, considering a baseline defined as a neutrality at the CaO over Si2 ratio of 1. Now, this led to an observation that the acid refractories are more compatible with acid slag or vice versa. Now, there are another more complex definition of acidity and basicity for high temperature chemistry than those given previously. Like in steel refining, the term V ratio is used where a ratio exceeding 1.0 implies a basic chemistry and the ratio below 1.0 implies acid. Now, this V ratio, question arises that how we can define the B ratio or how we can express the V ratio. So, the V ratio is expressed as V is equal to CaO plus MgO plus FeO plus MnO plus and so on over SiO2 plus P2O5 plus Al2O3 plus Fe2O3 plus Mn2O3 plus and so on. In many cases, it is convenient to use the 3-component phase equilibrium diagram in analysis of corrosion situation. The major refractory component can be visualized as one apex of the triangle with CaO and SiO2 as the other component. Now, in this analysis, it is convenient to use the simple CaO over SiO2 ratio. The refractories are rarely in chemical equilibrium on microscopic scale since they are typically made from mixture of different minerals. Now, second fundamental principle on porosity and corrosion rates. Most refractories contain wide spaces or porosity. This may be open pores that can be penetrated by a fluid media, that is apparent porosity, or it may be closed porosity that is not easily penetrated by fluid media. Now, if a refractory contained no porosity or brick joints or expansion joints or construction joints, the corrosion reaction is limited only to the phase exposed to the corrosive media, that is called the hot phase. Now, when porosity is present, particularly when open porosity is there, the corrosive material or corrosive media can penetrate the refractory, causing the destructive reaction behind the hot phase. The slag corrosion rates increase linearly with the percentage of apparent porosity within the refractory, and that is a porosity range from 12 to 16% apparent porosity. The higher density refractories exhibits lower wear rates and less spalling resistance, leading to higher wear rates by another process such as thermal shock. Now, the corrosive fluids can penetrate the refractory and result in the disruption and destruction of matrix of the refractory. Now, the matrix is the area of sintered fines and that hold together by bonded bricks and monolithic refractories. Therefore, the corrosion affects the weakest component of the refractory at higher rate than the denser or higher purity particles. Detailed description of corrosion. Now, it is obvious that the reactive component, hereafter called the slag, that must contain the refractory exposed surface or hot phase at an elevated temperature. Now, it is at this interface that corrosion begins and continues throughout the life of the lining. Now, the situation we can understand by considering a cross section of slag and refractory interface. Now, the refractory has a temperature gradient from the hot to cold phase, meaning that the highest temperature is at the hot phase and the temperature declines across the refractory thickness towards its back or cold side. Now, here you see the cross section of slag refractory interfacial area. Now, the slag shows penetrating refractory until the freeze plane is achieved. Now, the freeze plane is the location in the refractory where the temperature is sufficiently low to cause the to solidify. Now, slag reacts with the refractory, forming new phases at the immediate hot phase. Now, reactions may also take place behind the hot phase where the slag contact the refractory at the pore walls. Now, third fundamental principle of reaction and temperature gradients. A key concept of this particular principle is that the temperature gradient affects the extent of phenomena seen in the slag corrosion. Now, in a very steep temperature gradient, a very little penetration of slag is seen, with corrosion reaction more or less restricted to the immediate slag and refractory interface. The mobility of fresh slag, sometimes referred as a reactant to the slag refractory interface, may be limited, and transport of reaction products away from the slag refractory interface, that may be slow. The steep gradients can be seen in the thin wall refractory lining, such as those used in the utility boilers. Now, here you see that thin wall or steep temperature gradient. The corrosion situation in the thin wall refractory lining, this is particularly shown in this particular figure. Now, here the refractory corrosion reaction occur primarily at the intermediate hot phase, and then there is a little or no slag penetration. Here you see that this is the slag zone, and you see that particular phenomena in this particular figure. Now, microscopic examination usually shows that the penetration is confined to a depth of less than 100 microns or 0.1 mm behind the exposed hot surface. Now, this situation may be called as a stage 1 or slag attack, where the reaction occur at the intermediate hot phase. Now, it is found that the hot phase temperature primarily affect the rate of corrosion reaction. Now, if hot phase temperature is held just below the point that the product of corrosion become liquid, corrosion will be very slow or non-existent. So, most of the authority, they believe that if the hot phase is maintained at not more than say 20 degrees Celsius above this melting temperature, that is called the lowest eutectic temperature, reasonable corrosion rates will be observed. However, when the hot phase temperature is more than say 20 degrees Celsius above the eutectic temperature, then corrosion is rapid. Now, thin wall refractory design, rarely this exhibits more extensive corrosion phenomena than the described as stage 1 of the corrosion. The primary process variable affecting corrosion is hot phase temperature, secondary are the slag impingement velocity and slag chemistry. Now, let us talk about the thick wall, that is relatively broad temperature gradient. Now, thick wall refractory design begin to exhibit corrosion on their initial coating of slag at elevated temperature. In time, extensive corrosion of the refractory takes place, so that the refractory at stage 2 of corrosion. Now, stage 2 is characterized by two phenomena. One is the full penetration of the refractory, and second is the extensive disruption by corrosion of the hot phase region. Now, stage 2 follows stage 1 only if there is a sufficiently broad temperature gradient to allow penetration. Now, here you see that the stage 2 of the corrosion process, this showing a bonded refractory. Now, in stage 2, the coarse aggregate in the bonded refractory exhibits penetration particularly along the grain boundary. Here you see that the corroded aggregate, and this matrix is substantially disrupted at the hot phase. Now, the direct bonding between the matrix and aggregate particle is disrupted, but this bonding still exists. Now, the slag penetration in stage 2 can result in densification spalling. This type of spalling occurs because the thermal expansion coefficient in the slag penetrated zone is different than that in the unpenetrated cold phase region. So, on continued thermal excursion, maybe cooling or heating, spalling can occur at the line of demarcation between the penetrated and unpenetrated areas. The residual lining after spalling then begins the corrosion process anew, progressing from stage 1 to stage 2 again. Let us have a brief outlook about the stage 3 corrosion. At the end of the refractory lining's life, or in case of relatively slow corrosion rates, whereas the densification spalling has not take place, the refractory hot phase zone may progress to a final stage of corrosion that may be called the stage 3 corrosion. In this particular case, the bonding in the hot phase region and up to say 2 to 4 mm behind the hot phase is minimal. The slag itself appears to be the only phase holding the residual aggregate particles in place. Now, this is probably a result of higher viscosity in the slag in hot phase region and created as a consequence of dissolution of the refractory in the slag. Now, here you see the stage 3 of the corrosion process. Here you see that the relic coarse aggregate particles, and this one is the eroded particles. Now, the influence of slag viscosity maintaining some coherence in the hot phase zone in stage 2 and 3 with the thick wall design, a key process variable affecting corrosion rate is hot phase temperature. Many investigators recommended a hot phase temperature not more than 20 degrees Celsius above the solidus temperature between the slag and refractory zone. So, in this particular chapter or in this particular lecture, we had discussed about the various thermodynamic concepts pertaining to the refractory operation. Apart from this, we had discussed about the corrosion aspect in the refractory, and for your convenience, we have enlisted several references, and for further reading, you may utilize those references. Thank you very much.